Good morning. We were discussing the two-stage op-amp, which consists of any of the single-stage op-amps that we have had so far, plus a second stage, which because it has a single-ended input and single-ended output, can be a common source amplifier with an active load. And typically, if you have an NMOS input pair, you can use a PMOS common source amplifier and vice versa. But if you have something like a folded cascode first stage, then you can use either one. It doesn't matter because it will accommodate the swings. Okay. So I'll continue with our simple first stage followed by a common source second stage, and this can have, I'll show only a load capacitance, but it can also have a load resistance. So one thing to keep in mind is that you have to choose the bias point properly. That is, I think you're already familiar with this. Dual supply and single supply operation of the op-amp. That is, if you look at the sort of prototype op-amp circuits, you will see pictures like this. You will have the, let me show both the inverting and the non-inverting amplifier. So this will be connected to what is called the ground, and okay, similarly here. Okay, this will be the input voltage, that is the signal output voltage. Okay, and the op-amp itself does not have a ground terminal, right? The op-amp supplies just consist of some upper rail and some lower rail. Now, if you, so here, when you write something like this, it means that when Vi is 0, Vo is 0, so this is at 0 volts with respect to this ground. Okay. Now, obviously, both the input and outputs of the op-amp, input common mode and the output of the op-amp must satisfy the swing limits. The swing limit will be somewhere between the rails. Usually does not reach the rail, but especially the output swing cannot reach the rail. It will be somewhere between the rails. So this means that the op-amp is operating with what is known as dual supplies. This ground here, these are basically the same as that one. Okay. So you have some positive supply voltage and a negative supply voltage. I'll make them equal, not necessary for them to be equal, but that's a typical symmetric case. You may have built circuits in the lab with this plus minus 5 volts or 15 volts or whatever for op-amps. Okay. So the op-amp itself does not have anything called ground. Okay. It's a bias point that you choose. Ground is the common reference node in the circuit. So this is with dual supply operation. Now the same can be done with, let's say, a single supply voltage. So let me redraw both the amplifiers again. And this is typically how we depict circuits in CMOS. By the way, you can take any circuit as far as simply drawing the schematic is concerned, you can redesignate some other node as ground. It doesn't matter, whichever. It's like nodal analysis, you want some node as reference, you can choose any node as reference. In practice, what happens is that typically some node with respect to which you measure all the voltages and then to which lots of things are connected, that will be the ground. Okay. And there are systems in which, I mean, there'll be some big metallic chassis like in an automotive, this thing. So whatever is connected to the body of the automobile, that will be the ground. Okay. So it makes sense to do that. So typically the lower rail is the ground in most modern circuits. Okay. In CMOS circuits. It doesn't have to be like that. So this, for the supply voltage to be the same, this will have to be 2 VDD. Okay. Because the op amp is, the difference between the upper and lower rails is 2 VDD, right? And then here, we can still make the inverting amplifier and the non-inverting amplifier and connect the loads. Okay. So now, for these two circuits to be equivalent, okay, what should all these be? So they have to be biased again in the same way, like you have the two rails, and between the two rails you have to bias them somewhere. And to bias them in the same way as in the upper circuit, these have to be, this is VDD, okay. This will be VDD plus VI, and at the output you would get VDD plus VO, okay. Sorry, VDD plus K times VO, whatever that K is, depending on the resistor ratio. Similarly here, this is VDD plus VI, and this will be VDD minus some K prime times VI, okay. Right. So if you look at the signal currents flowing in the resistors, they'll be the same. They are not dependent on the bias point, okay. So don't get confused between these two. In prototype op-amp circuits, you will see what you see in the upper one. You would just see ground, right? Everything biased at ground. That is convenient in the sense you have only the signal without any, with a bias value of 0. But that needs dual supply operation. Or in a single supply, you can do the same, but these will be biased. Finally, it's all the same. I mean, you will need a supply to bias this, and you need a supply to power the op-amp. Okay. So now in our op-amp, we'll be using only the single supply model. Okay. We'll be using only the single supply operation. So now, if you want to connect a load resistor, this should not be connected to ground, because then this will be at some non-zero voltage and you will have operating point disturbed from this. So you have to choose the operating point for the op-amp, and this side should be that same operating point, so that with no signal, no current flows through the resistor. Okay. I'll remove it for now, but basically this is, I'm showing the op-amp with single supply. And we already saw the characteristics of this, and this is 2I0, this one, let me just call it I12, that is the current of the second stage, and this will be biased from a current mirror. Okay. So many of the characteristics are pretty straightforward. The gain is the product of the gains of the two stages. And if you do have a resistive load, what happens is the gain of the second stage reduces, but the first stage is not affected. So you could have a resistive load here, Whereas with a single stage op amp, it's not reasonable to operate with a resistive load because the gain reduces too much. Here, maybe, okay, you let the second stage gain reduce to some relatively low value, let's say 5 or something. But you can use a cascade first stage to get a lot of gain. Okay. So when you want to use drive resistive loads, pretty much the two-stage op amp is the only reasonable option. Okay. And because we have analyzed this sufficiently with the current control sources, we know that the unity gain frequency is GM1 by CC. The right half plane 0 is at GM11 by CC. And also the non-dominant pole, that is the non-dominant pole related to CL. In a real circuit, there will be more, right? There will be, first of all, this one I'll show. It is GM11 with some, if you have some parasitic C1 there, it will be GM11 times CC by CC plus C1. That's the fraction of GM11 that appears as conductance divided by CL plus the series combination of, okay. But remember, I mean, whatever non-dominant poles are there in the first stage itself, all of them will be here. So in this particular case, you will have, what other non-dominant pole will you have? When we did it with only control sources, we modeled this entire first stage with just a single voltage controlled current source. But we have analyzed this circuit itself, right? So we know it by itself has some non-dominant features. What are they? This first one, does it just like, does it act just like a transconductance GM1 or are there some additional factors? What is there? What else was there? Basically, there is a, if there is a parasitic capacitance there, then you will have a pole and zero because of that, right? Right? So those things will still remain. It will be essentially, instead of GM1, you should have GM1 of S. Okay. So if you use a cascade first stage, you know that there are many other nodes, right? There are 4 extra nodes, the cascade nodes of the input differential pair and the current mirror, and each of them will contribute a non-dominant pole at least, and all of them will appear in the overall transfer function. Of course, the point is not to sit and calculate the values of all of them. You need to know that they are there. So when you look at the transfer function, you do expect some change in the stability margin and so on. Okay. Any questions? So these are the sort of small signal characteristics of the op amp, and we can continue with that. What other, I think this is basically, yeah, these are the small signal characteristics, right? Now, noise and offset, what do you expect? What do you expect will be the noise and offset of this two-stage op amp? So basically, whenever you have multiple amplifier stages, so let's say this, I'll write it as VN1, but the same applies to offset also. VN1 is the input referred offset of A1. And then VN2, this is the input referred offset of A2. Okay. So now this is equivalent to, as far as the signal is concerned, a gain A1, A2. And what is the input referred offset? What will be the input referred offset of this composite thing? This will be Vn1 plus Vn2 by A1. Okay. So obviously, if Vn1 and Vn2 are comparable and A1 is reasonably large, the effect of the second stage is negligible. Okay. We will assume that anyway we design the first stage for a high gain here. So for both noise and DC offset, we will neglect the contribution from the second stage. But of course, you have to be aware that the second stage is there, and maybe in some weird design corner case that you have, you will find that the second stage is significant, and then you will have to work it out. Okay, I mean, you will have to work out what to do to reduce that. Now, given that it is only from the first stage, so this okay, given that it is mostly from the first stage, we already know the results. Just for reiteration, what is the input referred noise spectral density? What is it? What is it? 16 by 3 kT by GM1 1 plus GM3 by GM1. Okay. And similarly, the input referred offset variance is okay. So it's exactly the same as what we had for the single stage op-amp. We'll assume that it's the same result because I mean the second stage's error will get reduced by the first stage gain. Okay. Any questions here? Now this is about noise and random offset. So let's say that first bias the op-amp in open loop at VDD by 2. We never do this. This is just for analysis. Okay. Again, in absence of any mismatch, what will be this voltage? It is VDD minus VSG3 at a current of I0. Basically, these two will be the same. Okay. Now, what will be the output voltage? What will be the output voltage? Okay. If I gave you this circuit, okay, this is M12, M11. Will you be able to find the output voltage? Why not? Will you be able to find the output voltage or no? what will you do? How will you solve for this? How will you go about doing this? Yeah, you can do it graphically. Now, which region will the transistors be in? Saturation. One in triode, one in saturation. Why? Which one will be in triode? Yeah, so maybe you can make it more precise. So what will you calculate first? I mean, they cannot be carrying different currents. Obviously, they are carrying the same current. So what is it that you mean? Right. So that we can solve, but to find out which one will be in triode, so to equate currents, you have to use the appropriate current equation, either triode or saturation. So how will you find out which one is in triode, which one is in saturation? Yeah. Yes, Chetan. Yeah. Basically, yeah, like he also said, you find the saturation current of M12 with the gate voltage of VGN. You find the saturation current of M11 with a gate voltage of VGP. I mean, source gate voltage of VDD minus VGP. Okay. So you then what? What after that? So you will find ID of M11 with a source gate voltage of VDD minus VGP, and you can also find ID of M12, that is, let me say, saturation current. ISAT 11, ISAT 12 with a gate source voltage of VGN. Well, how will you decide after this? Okay, I found this out. That is easy to do, right? That is saturation current. We use the right formula. Then, yeah, if they're not same, what is that? So, a MOS transistor with a given gate source voltage, it can support a current up to the saturation current. Okay, the current can be less than the saturation current, but it cannot be more. So, you find the saturation current of these two cases, right? Whichever is the higher one, we can move to the triode region and carry the same current as the lower one. Okay, that is basically what happens. And this is the same as essentially doing it graphically. So, the NMOS's output characteristics, ID versus VDS, may look like that. And the PMOS's ID versus VDS, we reflect and mirror about VDD, right? And depends on how it is. If its saturation current is smaller, then the NMOS can go into triode region and support that current. If its saturation current is larger, then PMOS itself has to go to the triode region so that its current come down to the NMOS saturation current. And if both are in saturation, then the operating point is likely to be somewhere in the middle. Okay. So if you connect two sort of current sources like this, ideal current sources, you can't tell what that voltage is anyway. With real current sources, you can, but whichever has the higher saturation current will drive itself into triode region. Okay. So this is something that you should know, right? So now there is some, if I call this M00, this is VG00, and the same is applied to M12. With this gate voltage, this will have some saturation current. With this gate voltage, which is determined by the first stage, this will have some saturation current. Okay. So now, if you just connect it in open loop, this could be at the near the upper rail. if M11 tends to carry more current because M11 goes into the triode region or near the lower rail. Okay. Is this fine? When you just have an open loop op amp, this can happen. If the saturation currents in M11 and M12 are unequal, then one of them will go to the triode region. Okay. Now let's say that I12, this was greater than the saturation current of M11 with that voltage. So the output is close to ground. Okay. So now what I'll do is I will remove this and close the feedback loop. What happens? You understand? I am saying that if both the inputs were biased at VDD by 2, the output was close to ground because the NMOS tended to carry, NMOS had a higher saturation current. So now I close the negative feedback loop. What happens now? Gate of M11? Yeah. So obviously, initially, if this voltage starts from a very low value, what happens is this will come down. Okay, that will increase the current through M11. Okay, basically it will stop when in this case, obviously, again, the current through this and the current through that must be the same. Now, what is this? This is just the op amp in. All I have done is this, right? And this is VDD by 2. What should be the output ideally? What will it be in reality? What will it be? Well, you're assuming that that is still operating in the linear region. You can't tell, but basically this voltage has to move by certain amount, okay, so that these two currents become equal, okay, and that delta divided by the gain of the first stage has to appear across the first stage inputs. Is this clear? I mean, you need to have some delta V here so that this voltage reaches the right value. Otherwise, it cannot happen at all. Okay. This is, I mean, last time we talked about the systematic offset, right? This is the systematic offset in two-stage op amps, and it will almost certainly be there. Okay. Because you expect that if you put it in unity feedback, the output will be at VDD by 2. But now, because naturally it was somewhere near ground, to lift it up to VDD by 2, you need to have some difference between these two. Of course, if you have a very high gain first stage, then the difference is very small. Okay. Is this okay? Is this clear? So you need some gate voltage for M11 to make its current equal to the current of M12. M12 is fixed, right? In this particular case, M12 is a fixed current source. Okay. M11 is the one that can change through negative feedback. Okay. So M11's current changes itself to itself to become the same as that of M12. Okay. For M11's current to change, its gate voltage must change. Its gate voltage is the output voltage of the first stage. So if the output of the first stage has to change, the input has to be non-zero by some amount, which you can figure out. Okay. Is this fine? Now, to minimize the systematic offset, what would you do during design? What's that? High gain. Okay, fine. That may be not possible to increase beyond a certain value for, let's say, whatever reason. What else could you do? Huh? Similar? So basically, you design, if possible, so this you have to design it so that the saturation current of M11 with whatever voltage is given by its input equals the saturation current in M12. If you do that, you reduce this possibility. Otherwise, if the currents are very different, one of them will be in the deep triode region and it takes more voltage to bring it back. Okay. Now, this may or may not always be possible or even desirable, but that's something that you can do. Like I said, you get a scenario where you are operating, your output is more somewhere in this region rather than deep in the triode region. That's all. Okay. So, you will have systematic offset because but if you had that saturation currents equal by design, that movement is small and then you have lesser systematic offset. Okay. You have to see if this is a real problem, you have to solve it, but this is something that you may encounter. That is, you may have designed an op-amp with a very high overall gain. Okay. And then you connect it in unity feedback, you don't have any mismatch, you simulate it, you will find that the output minus input is not zero. It's not some very small value either. It can be because of the systematic offset. Okay. With whatever voltages that tend to exist there. Any questions? So now, of course, we have the two-stage op-amp. It can be biased, and we know the poles and zeros. So the small signal stability stuff is all taken care of. Now, about the swing limits. Again, as usual, for this type of op-amp, you have what will be the input common mode swing limit of this op-amp? Which stage will determine this? Which stage will determine the input common mode swing limit? First stage. I mean, it's the same as what we had for the simple single stage op-amp, right? This is just and on the lower side. This is for this particular stage, but whatever type of stage you use, it will be corresponding to that. Okay. So if you, I mean, it's only this part that plays a role in limiting the input common mode swing. If this input voltage becomes too small, then M0 will go into the triode region. If it becomes too large, M1 and M2 can go into the triode region. Okay. What about the output swing limits? Which transistor gets in trouble if the output increases too much, if the output goes too high? If it goes too low? Yeah. So there is no, this is quite simple, right? So what is the lower limit on the output? This is the output voltage. What is the lower limit on the output? VD sat 12. Upper limit VDD minus VD sat 11. That's all. Basically, you have to leave enough room for this transistor and that transistor. Okay, this is the best. I think I have mentioned this a few times. This is the best type of swing limit you can get. The upper limit is 1 VD sat from the upper rail, and the lower limit is 1 VD sat from the lower rail. Okay, I have assumed that what limits the swing here are the voltages. There can be cutoff limits also. Okay, that is, if the when do you have cutoff limits? When there is a substantial current swing in the device. Okay, so you have some operating point current, you have some signal current on top of it. If the sum goes to 0, that's when you say it cuts off. Okay, so now this cutoff limit, uh, yeah, this will happen only if there is substantial current swing. In fact, right now I don't have any substantial load here. I have not taken that into account. So if you have a very heavy load, if you have a load that draws a lot of current, then cutoff also may come into the picture. That is, you can't take the operating point currents through the output transistors. You may have to consider the fact that the currents change. Okay, which devices current changes? If you have a load, which current changes? M, which one? M11. Yeah, this is a fixed current, right? The current through M11 will be the load current plus this fixed current. So it's only the current through M11 that changes, and it's possible that it can go into cutoff region. We won't consider that for this, right? For the voltage swing limits, I have not considered that. Is that okay? Any questions? What other large signal quantity is there? Slew rate. Okay. So to evaluate this, I will consider this model, which anyway, how we derived the two-stage op-amp in the first place. Okay. Now, what do I mean by this model? I mean, this makes it very clear that we were driving essentially a second stage, which is a current controlled voltage source, right? Current controlled voltage source whose transimpedance is 1 by SCC, okay, through this. So what is the, so basically the second stage itself is a negative feedback loop. So what is this voltage? Approximately. What is that voltage? The second one is a negative feedback implementation. So what is it? 0. So this is approximately 0. So we'll assume that the incremental voltage at the output of the first stage is nearly 0 for this analysis. Okay. So this is for analyzing the slew rate. Okay. So now I will apply a step, the differential voltage. This is a step. Okay. So what will be the current output of GM1? It will be GM1 times VD. Okay. So what will be the output voltage as a result of that? What is the output voltage as a result of that? So the output voltage, you expect it to be a ramp with a slope GM1 by Cc times the input step. Okay. So now the current flowing through that will be, so this is approximately 0, right? So the current flowing there will be Cc okay. What will be the current flowing through the load? What will it be? It will be CL times the derivative of the output. What is the current flowing out of the second stage? What will it be? 0. Why? No, that is because of negative feedback, right? The idea of the negative feedback is this will deliver whatever current it needs so that it maintains it at 0. Otherwise, the current output of every op amp will be 0. Okay. So what is it? It is the sum of these two currents, right? You have that current and that current. So it will be Cc plus Cl dV naught by dt. Okay. Right? Okay. So now let's keep this in mind. Basically, the second stage has to put out Cc plus Cl dV naught by dt, and the first stage should pull in GM1 times Vd. Okay, which is also the same as, by the way, if you just look at this, GM1 times Vd is simply Cc times dV naught by dt, right? Okay. So we know that, I mean, the voltage swing limits come because of voltage limits, right? And then the slew rate is because of the current limits of different stages. So now the first stage current output is Cc times dV naught by dt, and second stage current output is Cc plus Cl times dV naught by dt. Okay. Now, what is the limitation on the first stage current? How much current can be pushed out of the first stage? 2I naught. How much current can be pulled into the first stage? Huh? Also 2I naught, right? So basically, this Cc times dV naught by dt should be between minus 2I naught and 2I naught, right? That is the maximum current you can get out of the first stage. So whatever current we saw that basically this Cc times dV naught by dt is what has to be pulled from the first stage, right? And that has to be between plus minus 2I naught. Is this part okay? Okay. What is the current limitation of the second stage? That is, what actually, where is the limit coming in? What is the current through M12? It's always I12. Uh, there is no change at all. What is the current through M11? What is the current through M11? I mean, this is Kirchhoff's law, right? What is the current through M11? So it is the current through M12 plus the one through Cl plus the one through Cc. Okay. So the second stage current is, I mean the current through M12 would be I12 plus that whole thing, right? Maybe I'll write it separately. So okay, this is fine. Is okay? So what is the limitation? Is there any limit imposed on this, or you can have any value? The first stage we said it can put out a maximum of 2 I naught and draw in a maximum of 2 I naught. What about the second stage? Or in this case, I've expressed it as current through M11 because that's the only thing that's varying, right? So what is the limit? Is there any limit, or we are okay with any value? What is the limit on the current through M11? Should be? Why? Where do we get current related swing limit? What is the region that we are concerned with? Okay, so that means what is the limit? Yeah. What is the limit? Yes, Kirtana, what is it? It should be greater than 0. That's all. Okay. If you have 0 current through M11, there is no second stage. Okay. That is, the second stage is completely off. So very crudely, the limit is simply greater than 0. Okay. So you get now two different limits. So this one says dv naught by dt must be the negative limit will be minus 2 I naught by Cc and the positive limit will be plus 2 I naught by Cc. Okay. Whereas here, what does it say? Okay. Is this okay? So normally the slew rate is defined as a positive quantity. That is, you just say negative slew rate is something, okay, some positive quantity. So basically here you can see the second stage limits only on one side. Why is that? Because you can keep drawing more current. That is, if this voltage is increasing, right? If the output voltage is rising, what happens is that more current will flow into CL like this. Okay. So the current in M11 will be more than the bias current. Okay. So more than the bias current is okay. How will it supply more than the bias current? This voltage has to reduce. Of course, this voltage will not exactly be 0, but essentially there is no hard limit. Eventually there will be a limit. You can't reduce this indefinitely, but there is no hard limit like that. On the other hand, if this output voltage is falling, what happens is CL, it is pushing up current like that. CC is also pushing current like that. At some point, the current through CL and CC will become equal to I12 and this will cut off completely. Okay. So there is a limit only for the falling voltage in this case, right? So clearly, you can now see that the positive slew rate is 2 I naught by Cc. This is basically that one. And the negative slew rate is the minimum of 2 I naught by Cc and I12 by Cc plus Cl. That is, it could be limited by the bias current in the first stage or the second stage. And these refer to this one and that one. Okay. Is this okay? So because we have two stages, it could be, I mean, this is not very strange, right? When you evaluated voltage swing limits, you had cases where this transistor was limiting the upper swing limit, some other transistor was limiting the lower swing limit, and so on, right? And they could be from different stages also. Here also it is the same. The first stage is limiting the upper swing limit, positive slew rate, whereas the first or the second stage could be limiting the negative slew rate, depending on the current values. Is this okay? Please think about these. We'll wrap this up in the next class and move on to fully differential op amps. Any questions on this? So the two-stage op amp signal behavior, I think you already knew. Now, but it is actually a good thing to separate the small signal behavior and this transistor level biasing, etc., etc. So now we have filled in the transistor level details. Okay. In fact, with this, you can go on expanding the increasing number of stages, right?